But before that, just to recap what we did last time towards the end with respect to this reduced density operator, right? So we said that the way to think about the local states, right? This is the global description of the system. And of course, recall that this means 0A tensor 0B plus 1A tensor 1B, right? And the way to think about the local states is to do a partial trace operation. And partial trace basically gives you the local states, which could in general be density matrices. They need not be pure states, right? And this density matrix is obtained as trace over B of the joint state rho AB. And in this case, the joint state rho AB is simply this density operator, right? Which is the projector onto this pure state. So note that the bipartite state, so for the case of, so of course this is one of the Bell EPR states, and for the case of any of these Bell states, the bipartite state is pure, right? In fact, of course, it's a pure entangled state, right? But the local states, which you obtain by doing this partial trace, I asked you to work this out last time, right? So you basically had to do trace over B of half 0, 0, 0, 0 plus half 1, 1, 1, 1 plus half 0, 0, 1, 1 plus half 1, 1, 0, 0, right? This would be the density matrix corresponding to this. Remember, we worked out the bipartite density matrix last time. It's a 4 cross 4 matrix with 2 diagonal entries and 2 off diagonal entries, right? And so when you work out the partial trace over the B subsystem, what happens? I'm just again going through this. Very important for you to be able to do these partial traces. So if you have any doubts, please ask me. I'm taking the half out, right? There's a common factor of half. And then I have basically 0, 0, tensor 0, 0, right? That is what this term is. One is in subsystem A and the other is subsystem B, plus 1, 1, tensor 1, 1, plus 0, 1, tensor 0, 1, plus 1, 0, tensor 1, 0. Okay. Please do this math with me, and if there are any doubts, please ask me. Okay, as always, this is A and this is B. And now it's very easy to do the partial trace over B because you know that the trace of an outer product like this is simply the inner product of these two vectors, right? So this trace is 1, this trace is 1. What about these two terms? What do these two terms contribute?
0.
Indeed. So these two terms contribute 0 because the partial trace of 0, 1 or the trace of, outer product of 0 with 1 is 0, right? So this then simply gives me half trace B 0, 0 is 1, 1, 1 is 1. So this just gives me 0, 0 plus 1, 1, right? And what is this density matrix? Remember, this is the identity operator for a single qubit space. So this is the I by 2 density matrix. Do you recall where this density matrix was located on the Bloch sphere?
Center.
Exactly. This is the state at the center of the Bloch sphere. And we gave this a name. We said this is the maximally mixed state. Okay. This is the maximally mixed state. So if you think about what has happened, I have, so of course, this is one of the reduced density matrices, right? This is the local state on A, right? This is the state on subsystem A. Similarly, one can show that the state on subsystem B, which is obtained by doing partial trace over A of this bipartite state psi AB, show that this is also indeed identity by 2, which is also the maximally mixed state. So the joint state, the bipartite state, sorry, the bipartite state is something which is pure, right? So in some sense, it's an extremal state. It's a state that would sit on the surface of the state space, right? For a 2-qubit space, it is not exactly a block sphere, but whatever is the corresponding analog of a block sphere, it will be the outer, it's on the outer boundary, right? So it's a kind of extremal state, if you think about it geometrically, but the reduced states are the opposite. They are the most mixed states, right? They are the most mixed. So this is a hallmark of an entangled state, that the whole has more information than the parts. I would say this is a signature of an entangled state, right? Where the whole actually has more information than the parts, and these Bell states form an extreme example of this, where the whole is a perfectly pure state and the parts are maximally mixed states, right? So this can be quantified. This amount of information in a state can be quantified via the entropy, right? So I'm just going to quickly define what is called the von Neumann, actually, no, I don't want to define von Neumann entropy now. So actually what I'm going to define is simply the Shannon entropy. I know everyone here is familiar with Shannon entropy. You've either seen this in the context of classical information, probability, or in statistical mechanics, etc., right? So the Shannon entropy of what, right? So if I take any density matrix, right? So for any row, a single system density matrix, it could be a bipartite density matrix, it doesn't matter. For any row, for any quantum state, right? Because a density matrix is always a diagonalizable matrix, we can define the associated Shannon entropy of its eigenvalues, right? So this is the Shannon entropy of its eigenvalues, right? So you know that rho can be diagonalized, right? So we know that rho can be diagonalized, and because rho is a trace 1 matrix, right? The sum over I lambda I must be 1, and the lambda i's must all lie between 0 and 1, right? These are all properties which just follow from the property of this being a density matrix, right? So this lambda i's of a density matrix in particular form a probability distribution, right? The lambda i's associated with the density matrix form a probability distribution. Right? And so you can always define the Shannon entropy of a probability distribution. Can someone tell me what this definition is?
Summation minus p log p base 2.
There's no p here. There's lambda i's.
Lambda I, sorry. So summation lambda I log lambda I.
Yeah. So this is minus lambda I log to the base 2 lambda I. Right? So this, everyone I hope is familiar with this definition, right? And this, in some sense, quantifies what I call the spread of the probability distribution. In this case, it's the eigenvalue distribution. By eigenvalue distribution, I simply mean the probability distribution that is associated with the set of eigenvalues, right? So one can also think of this as quantifying the spread of the spectrum, right, of this density matrix, right? So how does this help us? Now look at the, so let's look at again the example of one of the Bell EPR states. So look at the bipartite state, rho AB. The associated density matrix is this. Right? What is the Shannon entropy associated with this density matrix? So I call this H, right? So H of this joint bipartite density matrix. So what is the Shannon entropy associated with any pure state?
0.
Why is it 0?
Because the eigenvalue is 1.
Exactly. So this, remember, is a projection, right? What kind of density matrix is this? This is a projection. It's a projection onto a particular pure state psi AB, right? And so these projection operators have only eigenvalues 1 or 0, right? So what is the Shannon entropy of this? The eigenvalue distribution is essentially a delta distribution. It has only one non-zero eigenvalue, which is 1, and all the other eigenvalues are 0. So this Shannon entropy is 0. It is like a delta distribution or a point mass, what is often called a point mass distribution in the probability science. But now look at the reduced density matrix, which is rho A or rho B. Both of them are simply the maximally mixed states, right? So now this is already the spectral decomposition. So what are the eigenvalues of the reduced states? Yes. What are the eigenvalues of the reduced states?
1 by 2, 1 by 2.
Yeah, exactly. Half and half. So what is the Shannon entropy of the reduced states now? So these are your
Log 2.
eigenvalues, half and half. Yeah, sorry.
Log 2.
Exactly. So this is the Shannon entropy of a maximally mixed distribution. It's a Shannon entropy of a uniform distribution. What is the Shannon entropy of a uniform binary random variable? It's a binary random variable, right? There's just two. I mean, the size of these distributions is just 2, right? So it's half and half. So it's minus half log half minus half log half. So you will figure out that this is just. So what did somebody say the answer was? Log 2, right? But what is log?
Base 2, so 1.
Yeah, exactly. So this is simply 1. Okay. So I hope everyone can evaluate this simply from this definition, right? So you see, this is in fact the maximum Shannon entropy that you can have for a qubit system, right? This is the maximum Shannon entropy possible for a qubit state, right? So And this is also the Shannon entropy of this reduced distribution, right? So you have a scenario where you have a bipartite state AB, which has zero Shannon entropy, but you have its marginals A and B having maximum Shannon entropy, right? This is a situation you will not find in the classical world, right? It violates certain fundamental properties that people associate with classical Shannon entropy, right? So this is only possible because this is the Shannon entropy associated with a particular kind of density matrix, right? Okay. So this Shannon entropy, in fact, is what will be called the von Neumann entropy, right? But we'll define that later in the course. So for now, I just want to point out this contrast that we are therefore maximally, so I want to therefore again reiterate the uncertainty point of view that we are maximally uncertain about the reduced states, but some sense fully certain about the joint state. Okay. So, and this can be quantified and made precise via the Shannon entropy, right? Shannon entropy associated with the eigenvalue distribution. Okay, so what is the significance of this local versus global description? So we can again go back to the teleportation protocol. And examine it from this global versus local description point of view. So remember that we had these three systems. There was A1, A2, and B. A2 and B were entangled to begin with. This was the unknown state. We did a C0 followed by a Hadamard, and this was followed by measurements. And conditioned on the measurement outcomes, Bharat had to do some local gates in his system, right? And then the state psi was realized here, right? So remember this joint tripartite state that we wrote down, A1, A2, B at this point, right? Which is just before the measurement, okay? At this point. So this state is what I want to write down, okay? And if you recall from the notes of maybe 2 lectures ago, or I don't remember, it was just last lecture, but let me just recall the state simply from the lecture, right? So this joint tripartite state had this form, right? It was half, and then you had 0, 0, A1, A2, tensor alpha 0 plus beta 1 on B plus 1, 1. Let me go in sequence. So there was 0, 1. Since I'm not going to keep putting the subsystem all the time. Alpha 1 plus beta 0, 1, 0, alpha 1, alpha 0 minus beta 1, 1, 1, alpha 1 minus beta 0. Right? So this was the state before Anita did her measurement and announced the result to Bharat or communicated that result to Bharat, right? So the question is, what is Bharat's state, or what is Bharat's knowledge of this tripartite state? This is what, so the tripartite state, notice, is still pure, okay? This is a pure tripartite state, okay? So suppose this classical communication did not happen, right? At this point itself, is the state, can we consider that the state has been teleported, right? What is the local description in Bharat's lab at this point, after Anita has done these local operations, which is the C0 and the Hadamard, let's say she may or she may not have done the measurement, we don't know. We are sitting in Bharat's lab, okay? So what would be the local description in Bharat's lab? And that local description comes by tracing out Anita's qubits, right? So tracing out Anita's qubits, we get the local state of B, right? And what is this local state of B? So to get to this local state, you will have to first write down what the density matrix associated with this state, tripartite state is, right? So this will be trace A1, A2, row A1, A2, B, okay? Now, I need you to work this out with me very quickly, okay? This will really tell you if you've understood the idea of partial trace or not. So this becomes psi A1, A2, B, psi A1, A2, B, okay? Now, I can give some name to these four states just to make my life easier. So I'm going to call them, so I'm going to call this state as phi 1, this state as phi 2, this as phi 3, and this as phi 4. Okay. So now you'll have to tell me what is this partial trace that you get. Can you work this out? I'll give you a few minutes. So there are four states here. So when I write down this density matrix, I'm going to get 16 states. But do I need all 16 states when I'm evaluating the partial trace? So I'm going to have states like this. So I will have 0, 0, 0, 0 on A1, A2, tensor phi 1, phi 1 on B, plus 0, 1, 0, 1 on A1, A2, tensor phi 2, phi 2 on B, 1, 0, 1, 0, A1, A2, tensor phi 3, phi 3, plus 1, 1, 1, 1, tensor phi 4, right? I am also going to have terms of the form 0, 0, 0, 1, tensor something, okay? I will have 0, 1, 1, 0, tensor something, etc. Right? But I am not going to take the trouble to write down all those states. Why? So the reason I'm not going to take the trouble to write down the rest of the states is because I'm tracing out over this subsystems, both the qubits that are there in A's lab, right? So this trace is what? Yes? Are you guys
Zero.
still with me? Yeah, indeed. This trace is 0. The trace of any of this, so 0, 1, 1, 0, this is 0. Trace of 0, 0 with 1, 1 is 0, right? Trace of 1, 1 with 0, 1 is 0. So all the cross terms are essentially going to go away because all those partial traces will give me 0. Because the set of states I have in A's lab are a set of orthogonal states, 0, 0, 0, 1, 1, 0, 1, 1. When I take all possible outer products, only 4 of those outer products will have a trace. The other 4 have trace 0. So I hope this idea is clear. So then what is the reduced state in B? So I have only 4 states which are going to contribute. For all of them, the trace on the reduced the trace on A1, A2 is simply 1, right? Because they just project us onto 0, 0, 0, 1, 1, 0, 1, 1. So what do I get? I left a factor of 1/4 here. Okay, so I claim that the reduced state is simply 1/4 phi1 phi1 plus phi2 phi2 plus phi3 phi3 plus phi4 phi4. Okay, and remember what these four states were. So this is 1/4 alpha 0. So phi1 was alpha 0 plus beta 1. Phi2 was alpha 0 minus, alpha 1 plus beta 0, doesn't matter anyway. Phi3 was alpha 0 minus beta 1, and phi4 was alpha 1 minus beta 0. Okay. So can someone work out what this, and remember to take the outer products now. Okay. So can someone work out what this outer product turns out to be? Yes. So the first outer product, for example, will give me mod alpha squared 0, 0 plus mod beta squared 1, 1, right? Plus alpha beta star 0, 1 plus alpha star beta 1, 0, right? That's the outer product of phi 1 with phi 1, right?
Yes.
Now the point is, when you do the other outer products, there are two minus signs sitting out here in two terms. There is one term where the alpha and beta interchanged. So between all of this, I claim that all these cross terms are actually going to vanish. Because when there's an alpha beta star 0, 1 with a plus sign, there is going to be an alpha beta star with a minus sign at 0, 1, right? And that is sitting here, for example. There will be another term with alpha minus alpha star beta, and that is sitting here, right? So when you put together all of this, what is going to survive are only these so-called diagonal terms like 0, 0, 1, 1, right? And there's going to be 4 of them, and all of them come with a mod alpha squared and a mod beta squared. So there is going to be, I claim, so there's going to be, so, but notice that in 2 of them they'll be flipped. So there'll be a mod alpha squared 1, 1 and a mod beta squared 0, 0, and that will repeat twice. So anyway, I'm going to just write out the final answer, and it is for you to check that this is the case. All cross terms will vanish. I will have twice, so I will have twice of this plus twice mod alpha squared 1, 1 plus mod beta squared 0, 0. Okay. And what does this evaluate to? This evaluates to half mod alpha squared plus mod beta squared 0, 0 plus mod alpha squared plus mod beta squared 1, 1. And what is this? Mod alpha squared plus mod beta squared is what?
1.
Exactly. So what is this state? What is this reduced state finally? This is simply going to be half
Identity by 2.
0, 0 plus half 1, 1, which is simply identity by 2, which is the maximally mixed state. Okay. So no matter whether Anita does her measurements or not, until she communicates the outcomes of these classical bits, which I think we called M1 and M2, right? Until this M1 and M2 are communicated, it's only after that they are communicated that B has a deterministic pure state in his lab, and this state is exactly equal to the state that A was trying to teleport. But if those measurement outcomes are not revealed, then B only has as much information as if he simply had a maximally mixed state of a single qubit in his lab, which basically has no information, right? Because it's a uniform distribution. And what is more, you know that for a quantum density operator, you have multiple pure state realizations. This maximally mixed state can be written in various ways, right? And in particular, there is like no information about the alpha and the beta, which is the information that you want to communicate, right? So this has no dependence on alpha or beta. So all of that goes away, right? So until the classical bits are communicated, so unless the classical bits M1, M2 are communicated, B essentially has no information about the unknown state psi, which is to be teleported. So this again is to reiterate the point that there is no faster than light communication happening. There is no violation of causality happening, right? Because without the communication of these classical bits, B is in a completely mixed state, right? So there is really no communication that has happened until there's no information transfer that has happened until this classical communication has happened, and this classical communication is indeed very much bounded by the speed of light, right? So this often is talked about as an information causality principle, that although it appears that once A measures, right, once these measurements happen, somehow B state has collapsed into something, information about this collapse does not propagate to B unless these classical bits are communicated. And without knowledge of those classical bits, B simply does not have information about psi. In fact, B's state is completely independent of psi, right? There is no dependence of this final state on alpha or beta. Okay, is this idea clear? Any questions? So please work out this reduced state, okay? It is a slightly long exercise, but please work this out so that you become familiar with how to do these partial traces and get the reduced states, okay? And we've actually traced out two subsystems here, right? And of a tripartite state to get a single qubit state. Okay, so this was about...
Excuse me, ma'am.
Yeah.
Ma'am, you made a statement. I mean, you
Mm.
said that, I mean, even if A measures bits
Mm.
in her lab, right? Unless she communicate it to B, B won't have any clue about alpha and beta.
Yeah. Yeah. Because so that is what the reduced density operator is all about. This whole mathematical machinery of partial trace and reduced density operator is for us to have a formal description of what the local state looks like. If A communicates the outcome of the measurement, right, then B knows that B has to do certain local operations on his qubit, right? And then the state is a pure state in his lab, right? But to get this pure state description, he must know the measurement outcomes. If there is no classical communication, that's what I'm saying. So if you stop the protocol here and there is no classical communication, between A and B. Actually, it doesn't matter. You could even stop the protocol here, right? But the key point is if there is no classical communication between A and B, then at this point, B's local description is that of a maximally mixed state. If A does communicate the measurement outcome, then what happens? Look at this tripartite state. A essentially is telling B that, hey, I collapsed down to 0, 0. Well, then B knows that he has collapsed to alpha 0 plus beta 1. If A says, hey, I have collapsed to 1, 0, then B knows that he has collapsed to the state which I called phi 3. Do you understand? Does that answer your question, Neelkanta?
Yeah. Yes, ma'am. Yes, ma'am.
Okay? All right. So until this classical information is communicated, the collapse information is not being communicated. And if the collapse information is not communicated, the best you can do is to have a density operator description. In fact, that is how we introduced the idea of a density operator. We said, what if you do not know which outcome was obtained for a given measurement within a given subsystem also, right? You can only describe it as a probabilistic mixture of the outcome states. And that's exactly what is happening. And in this case, a probabilistic mixture of these outcome states is basically a maximally mixed state, right? That's what we just showed here, right? A mixture of these 4 states, phi 1, phi 2, phi 3, phi 4, is simply this maximally mixed state. Okay? All right. So let us move on now to talk about. So I introduced the Shannon entropy as one way of essentially quantifying how different the global and the local description is, right? And I said it is very stark for the Bell states where the global state has 0 Shannon entropy, but the local states have maximum Shannon entropy. Now, surely this cannot be the only example of entangled states, right? There should be other kinds of entangled states who should have entanglement somewhere between that of a product state and the Bell state. I kept referring to the Bell state as maximally entangled, and I said the product states are completely unentangled. So how do we quantify entanglement, right? That's what we come to next. And in particular, we are going to look at bipartite pure states. Okay? So I usually start this discussion by posing a question. So I like to ask this question. So consider, I'm going to give you 3 states and I'm going to ask you which of these 3 states has greater amount of entanglement, or which of these 3 states is more entangled. Or I don't know, order these states according to their entanglement. So let us say there is a state psi, which is 0, 0 plus 0, 1 plus 1, 1 by root 3. I'll call this psi 1. I have a psi 2, which is 0, 0 plus 1, 1 by root 2. And I have a psi 3, which is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 by 2. Okay? They are all bipartite pure states. A, B is implied. They all are normalized. They're valid states, right? Because this one is 1 by 3 plus 1 by 3 plus 1 by 3, which is 1. This is 1 by 2 plus 1 by 2, which is 1. This is all 1/4, right? Some of 4 times 1/4, which is 1. Valid bipartite pure states, right? So can you, even by looking at the state, can you first of all even tell me whether they are entangled or not? Are all of these entangled states?
No, ma'am. The last one seems to be a direct product of plus and plus.
Very good. So the last state actually is unentangled.
Excuse me, ma'am.
Sorry?
Is the order of entanglement is psi 2, then psi 1, then psi 3?
Meaning that this is greater, and so this is most entangled, this is second most entangled, and this is least entangled. That's what you're saying.
Yes, ma'am.
Intuitively, yes, correct. So that's what I'm trying to get at. But the answer you're giving me is based on some intuition, right?
Yes,
What is
ma'am.
that intuition? Yeah, so we will, the way, so the aim of the rest of this and the next lecture will be to translate that intuition into something more quantitative, okay? So first, let's look at psi 3, right? So let's look at psi 3 and observe that psi 3 is a direct product state. So I think Amog is the one who answered. So Amog, what direct product state is it?
Plus and plus one.
Exactly. So this is actually the state plus tensor plus, right? Plus is 1 over root 2, 0, 1. 1 over root 2, 0, 1. You take this direct product, you will see this is what you get. So this is actually unentangled, right? So by some measure, right, there must be some measure which should say that entanglement of psi 3 is 0, right? Or there should be some test which tells you that the entanglement in psi 3 is 0, right? Now again, because I kept saying that this is maximally entangled, it appears that this is the most entangled state. This is one of the, I mean, we've given this state a name, right? We've called it something. We say it's a Bell APR state. So this seems to be the most entangled state. And this seems to be somewhere in between the Bell state and the product state. But how do we quantify this? So the answer to this, first of all, lies in asking which basis is the state entangled in? Because you see, what have you done here in going from this description to this description? Essentially, you transformed something which was in the 0, 1 basis to the plus plus basis, right? Or if you think about it the other way around, what was in the plus plus basis was simply rewritten in the 0, 1 basis, and then you got this state. If you look at this state, this is a uniform superposition of all 4 basis states. But if I had given different weights out here, then this is no longer true. Then you no longer know whether you can actually write it as a combination of 2 product states or not. So this is essentially a basis change, right? So the key to understanding whether a state is entangled or not is to understand the basis in which the state is entangled. And this becomes manifest when we do something called a Schmidt decomposition. Okay, so that's what we're going to discuss. I will just state the idea today and we will prove it in Thursday's class. Okay, so what the Schmidt decomposition, the Schmidt theorem says is the following. So it says that given a pure state psi which belongs to some joint Hilbert space HA tensor HB, then there exist orthonormal states. So I should say local orthonormal states, right? So I'm writing 2 local sets now, EI, where I, goes from some 1 to K, let's say. This belongs to HA. And another orthonormal set, Fj, which belongs to HB. Again, let's say I goes from 1 to K. Sorry, J goes from 1 to K. Such that psi AB can be written as sum over I going from 1 to K, lambda I, EI, Fi. Okay, that's very important, EI, Fi, where lambda I are real non-negative numbers, such satisfying sum over I lambda I squared is 1. So this part, of course, comes simply from the fact that the state is normalized, right? In some sense, we can trace it back to that. But you see, the relation is sum over I lambda I squared is 1. Okay? So this is a special way of writing a bipartite state. It is a special way of writing a bipartite state such that the entanglement content in that state is manifest. Okay? This particular set lambda I are called the Schmidt coefficients. And the local bases EI and Fj are called Schmidt bases. Okay, these are, remember, local bases, meaning each one is a basis for A and B respectively. Of course, if you take a tensor product, you get a basis for the joint system. But when I say Schmidt basis, I mean Schmidt basis in A and Schmidt basis in B. Okay, so this is the content of the Schmidt decomposition theorem. It says that for every state, there must exist such a decomposition in terms of two orthonormal bases in A and B. Now, what is the key feature of this? Notice that the summation is only over a single index, right? When I write down a general description of a state in terms of two local bases, I need not have a single index, right? Typically, the sum will have multiple indices, two indices, right? So just to contrast, and I will stop with this. So just to contrast with the standard description of a state, if I have two local bases, let me call this BI, something else. Let me call this, let me just say that there is some local basis J, I and J. Let me just call, that's what I usually use, right? So I and J. So some orthonormal bases in A and some orthonormal bases in B, right? Then what is the general description of a bipartite state? This is going to be written as sum over I comma J, Cij, I A tensor JB, right? Because this basis, the joint basis is going to have all possible elements, all possible combinations of I and J, right? So this is the standard expansion of any bipartite state in terms of a basis for the joint system. So this Schmidt decomposition is not that. It is saying that from this general description, I can always go to a description of this form. I can always find an EI and an FJ such that the state can be written in this so-called diagonal form, where the summation index is just over one index. And when you do that, depending on how many of these Schmidt coefficients are non-zero, you can decide how entangled the state is. Okay? So what you did here, this basis change, right, which you did in a very intuitive way. You looked at the state, you said, oh, but this is simply plus tensor plus. So this is actually a Schmidt decomposition. This is the general description in terms of the standard basis, and then you rotated it to the plus basis, and you realize that if you try to do a Schmidt decomposition, there is only one non-zero term. There is no sum over, there's just one non-zero term, right? And this then revealed to you that the state is unentangled, right? So this is what we formalize, and we'll formally prove this in the next class. Okay? Questions? Okay, so I have a question for you guys. Are you familiar with the singular value decomposition? I don't know how many people are still in class. Okay,
Somewhat.
somewhat. So I urge all of you to please look up what singular value decomposition is before you come to the next class, and that will help you understand the proof of the Schmidt decomposition. So this should be there in Nielsen Chuang chapter 2, one of the linear algebra earlier sections. So please look up or refresh your memory on the idea of singular value decomposition. I'm sure across physics and engineering, you guys must have encountered it, but please go and refresh your memory. Okay? Yeah, there was a question.
Ma'am,
Yeah.
hello.
Yeah. Go ahead.
For a pure state, we may have systems with different dimensionalities, right?
Indeed. Very good. Yes. Yes.
So in that case, this K will be different now for the two systems.
So what the Schmidt decomposition then reveals to you is also this fact that if I have two systems with two different dimensionalities, how many non-zero Schmidt coefficients are possible? I am bounded or I'm constrained by the dimension of the smaller system. Correct? Because I cannot find more orthogonal states. So if A and B have dimensionalities D1 and D2, I cannot find more than D1 orthogonal states in HA and more than D2 orthogonal states in HB. Right? So in this case, K has to be whichever is the smaller, or at least K, let me put it this way, K is then upper bounded by whichever is the smaller of D1 and D2, right? If A is of dimension D1 and B is of dimension D2, then I can only have as many non-zero terms in this expansion as as I have degrees of freedom, essentially. So I am bounded by the smaller system dimensionality. So what this means is if I take a qubit, imagine a qubit interacting with a radiation field. Imagine a two-level atom interacting with a radiation field. The radiation field may have infinite modes, may have infinite degrees of freedom, may be an infinite dimensional system. But the amount of entanglement that can exist between these two systems is essentially bounded by the qubit. So I cannot have more than two non-zero Schmidt coefficients when I do an expansion of this form. And so I cannot have more entanglement than what is possible for a qubit system. Right? So indeed, that's a very beautiful aspect of the Schmidt decomposition, that it immediately tells you that you cannot have more entanglement than the dimensionality of the smaller system. And that is what decides what is the maximum possible entanglement. So in the case of two qubits, for example, this is maximally entangled because you cannot have more than a pair of orthogonal states for a single qubit, right? So that is what then decides that. So in this case, the dimensionality of both systems is 2, and that's why this is the most entangled form possible. Okay? I hope that answered your question, Nilesh.
But dimensionality is 2 for psi 1 also, na?
Sorry? Can you speak up louder?
Yeah, this psi 1 state here on the screen, this is also having dimensionality, right?
Yes, the point is, this is not in Schmidt form.
Oh, yeah, okay.
So in fact, this will be part of your homework now. This will be part of assignment 2 for you to work out what is the entanglement content of this state. And in order to do that, you first have to convert it to Schmidt form. And this is not even as simple as going to plus minus basis, no? Even in plus minus basis, it will have all possible combinations and it will not tell you. That's also not a Schmidt form. So you'll have to identify the right Schmidt basis. That is the challenge. Okay.
Yes, sir.
Excuse me, ma'am.
Yeah.
Wait. Someone said that dimensionality of psi1 state. I mean, we are associating dimensionality with a state. I'm a little confused here. We associate dimensionality with the system, right?
Yeah. So I think what he meant was that this is also a 2x2 state, but I'm having 3 terms here in this expansion. That's what he was confused about. See, these are all 2x2 systems, right? These are all states in 2x2 systems, right? So what Nilesh was trying to get at is this is also 2x2, and I said this is the most possible entanglement here because the dimensionality, I have maxed out the local dimensionality here, right? But in this case, there are 3 terms. Of course, there are 3 terms in the sum, but they're not in Schmidt form, right? This is 0, 0, 0, 1, 1, 1. The Schmidt form does not allow for these kind of cross terms, right? So that was the question. Do you understand, Neelkant?
Yes.
Yeah, we indeed associate dimensionality only with the system, and that's what I was trying to say, that you cannot find the Schmidt basis to be larger in dimension than the dimensionality of the system itself, right? The maximum size of the Schmidt basis that you can have is the dimension of the system. And so in the case of 2 qubits, the maximum size of the Schmidt basis you can have is 2. And in this case, the Schmidt basis is indeed just the 0, 1 basis itself. Okay?
So, I mean, just to confirm, so effectively we need to find a suitable Schmidt basis, right?
Yeah, for both subsystems.
Yeah, sure. Thank you.
Yeah. Okay, so I'll see you all on Thursday then. Stop recording and we'll prove the Schmidt decomposition on Thursday.